Hello, and welcome to our poster for Cosyne 2021 conference. First, let me walk you through the motivation of our work. Here, we study the very common problem of allocating finite sampling resources to determine the best out of several options. So our main questions are, what does it mean to decide optimally when resources are limited? What is the role of the environment in the capacity of the agent? Is there a good reason why is it good to ignore many of the options? Thus far, research in this area of multi-alternative decision-making has considered low numbers of available options. It is not very explicit about the limitation of the resources. So here in our accumulator model, we assume an environment that is producing many options characterized by this drift parameter mu, which is unobservable to the agent who has a finite resource T that they have to split and allocate to each of the options. Once they've done this, evidence accumulates in a drift diffusion fashion. And each accumulator integrates this evidence, and the agent has access to both the final evidence and the allocation policy. With this, they can optimally infer the values of each of the drifts and choose the best one, which maximizes the utility of the choice. But here, we're interested in the expected utility of the allocation. In other words, that the utility that the agent wants to optimize is the expected value of the maximum over the space of allocations. To do this, we first notice that the posterior distribution over the drifts depends on both the observation likelihood, here in orange, and the prior, here in cyan. And here we want to emphasize the variances, sigma squared over t for the likelihood and sigma naught squared for the prior. So we define this quantity, this dimensionless quantity capacity, simply as the ratio between the precision of the observations and the precision of the prior. So under this view, the capacity of the agent depends on how the resources are related to the environment. With this quantity, we are able to identify two regimes of optimality. So first, we examine the space of even allocations. That means that we are going to sample m options and divide the resources equally among them. So we find that when capacity is small, the expected utility can be approximated with this quantity here, regardless of the prior. And interestingly, this expected utility has a maximum at m equal 5, which means that the best thing to do is to sample 5 options. We've confirmed these results first through Monte Carlo simulations of this equation over here, and through numerical integration of analytical expressions that we find for various priors that we tested. Here, Gaussian, uniform prior, and a bimodal prior. On the other hand, when capacity is large, the prior starts playing a role, and the optimal number of options to sample grows as a function of capacity. So we've found in this work an analytical expression for the Gaussian prior, and we see that the red dashed line here approximates really well the blue one. So, okay, that was for even allocations. What happens when we can unevenly distribute our resources? Well, we find that since options are a priori indistinguishable, allocating capacity evenly between the options is optimal. And first, we see this when we define this trajectory over allocation space through these orange arrows, where we go from even allocation to even allocation. And we find that every time we hit one of these even allocations, squared, circle, triangle, and so on, we find a critical point of the expected utility. And we've confirmed through gradient descent that indeed this expected utility is maximized at one of these even allocations. So our main takeaways are that capacity is a quantity that depends intrinsically on the resources of the agent as well as extrinsically on the environment, which contextualizes the agent and tells us how well suited they are to solve a task in the environment. Okay, we also find that when capacity is small, the optimal policy is to sample 5 options, and this is independent of the prior. Now, when capacity is large, the optimal number of sampled options grows sublinearly with capacity, which means that with increasing capacity, there's an increasing emphasis of depth over breadth, where the emphasis specifically depends on the prior. Finally, we find that allocating our finite resources evenly between the options is optimal. So thanks a lot for listening. You can find these results at this link, and you can contact me with this email.